All right. All right. So linear programming is an optimization strategy for businesses and economics. Okay. The two-dimensional linear programming problems consist of linear objectives. Okay. And these linear objectives will be some kind of equation, and that will help us get to those maximum and minimum values that we need. Okay. Yesterday you talked about the 7.5, the linear system of linear inequalities, where we were able to graph and do our shadings and stuff. With these, in the linear programming, these linear inequalities are going to be our constraints. So it's going to put our boundaries on our objective. Okay. These constraints determine the set of feasible solutions. So before, when you looked at those systems of linear inequalities, you had tons of shading and it went on and on forever. So you had all of these possible answers, things like this. With these constraints that we're going to have today, it's going to put a boundary on. So if you look at example 1 here, all of these constraints actually bounds that shaded region. So now it's not an unlimited number of solutions. It is just a quantity of it. Okay. We have a smaller set of solutions instead of just a region. Okay. So to solve using these, okay, we're going to sketch a region corresponding to the system of constraints. Most of them are always going to be given to you, but we do know how to graph these and then find the point of intersection and then know which way to shade in that sense, especially with it being linear. It's a lot easier for you. We're going to find the vertices of the region, so where they intersect. Okay, so where those constraints intersect. And then we'll evaluate the objective function, okay, at each of those points of intersections, okay? And once you do that, the value will give us a minimum or maximum value will exist, okay? Now, if it is unbounded for some reason, like this equation doesn't exist, then the region keeps extending and extending, okay? Actually, it would probably more be this one. That would be an unbounded region. So you might not have a maximum value of it. You could still have a minimum or vice versa, where you might have a maximum, but you don't have a minimum because it keeps on going in one direction, okay? So looking at this, find the maximum value of z equals 3x plus 2y. So this is my objective. Okay, so that's my objective function, subject to the following constraints. Okay, so if I looked at y is greater, or x is greater than or equal to 0, that would be my horizontal, my vertical line, sorry, my vertical line right here, right? Greater than would be shade to the right. Y is greater than or equal to 0 is this here. We would shade above it. Now, x plus 2y is less than or equal to 4. Okay, you could either put it into slope-intercept form, okay, or you can find your intercepts and go from there. Okay, so my x-intercept is 4 and my y-intercept is 2. So we graph at 2, y-intercept's 4 here, so this would be that line here, less than or equal to, below. And then here, same idea, you can have your intercepts and it ends up being this line. Okay, so then when we shade, the intersection part would be constrained by all of these graphs. Okay, now here's our point of intersections. Okay, we have 0, 0, 1, 0, 2, 0, and 2, 1. Okay, now once you have those point of intersections, okay, we evaluate this objective function at each one of these values. Okay, so we want to find what our z is, and our z is going to give us our maximum or our minimum value. Okay, so looking at this, so let's go ahead and start at point, let's do 0, 0 first. What is my z at the point 0, 0? So we're going to have 3 times 0 plus 2 times 0, and we just evaluate. And what do we get?
0.
0. Yeah. Okay. So right now, that's a really low value, isn't it? So potentially that could be our minimum value in that sense. Okay. Now let's look at point with 1. Let's do 1, 0. So z equals 3 times 1 plus 2 times 0. So 3 times 1, 2 times 0. And what do we get?
3.
3. So right now, we know at 0.10, that would be a maximum value, but we haven't tried all the points. But right now from these, 0 would be my minimum, 3 would be my maximum. Okay, let's try the point. Let's do 2, 1. Z equals 3 times something plus 2 times y. So 3 times 2 plus 2 times 1. And what do we get?
8.
8. So right now that would be our maximum value, right?
Mm-hmm.
But we still have one more point to try. So our last point would be 0, 2. So Z equals 3 times something plus 2 times something. So 3 times, in this case, x is 0, y is 2, and we get
4.
4. Okay. So now looking at these, do we have a maximum value? It said find our maximum value. What can we conclude here? That our maximum value is Z equals what?
8.
8, yep. And that occurs at x equaling what and y equaling what?
2 and 1.
2 and 1, yep. And there you go. That's it. Right. Example 2. Find the minimum value. So now we're looking for the smallest number of z, where x is greater than or equal to 0 and y is greater than or equal to 0, subject to the following constraints. Okay. And here are all of those graphs. Okay. So I went ahead and graphed them now because x equals has to be greater than or equal to 0, y equals greater than or equal to 0. We know we're in the first quadrant there still. Okay. Is everyone okay with that? Now, if they give us the graphs, it makes it a lot easier to find those maximum and minimum values, doesn't it? If we don't, we'd actually have to graph all of these, right? And then find the point of intersections from that. Okay. Is everyone okay with that? All right. So now let's check our points. Let's do 0, 4 first. And remember my equation for z, my objective is z equals 5 times x plus 7 times y. So what do we get? My x in this case is 0 and my y is 4. So what do we get?
28.
28, good. Right. Let's try the point, let's do 0, 2. So z equals 5 times x plus 7 times y. X is 0 again, y is 2, and we get what?
14.
At the point, let's do 3, 0. I like getting the zeros out of the way. Z equals 5 times x plus 7 times y. Okay. My x is 3, my y is 0, and we get what?
15.
15. Okay.
15.
Yep. And then let's do you guys want to do 1, 5 or 6, 3 next?
6, 3.
6, 3. Okay, so z equals 5 times x plus 7 times y. So my x is 6, my y is 3. So 5 times
51.
7 times 3 is
51.
51. Good. And then the last point we have is 1, 5. So z equals 5 times x plus 7 times y. My x is 1, my y is 5, and what do we
40.
get? 40. Okay. So what did we learn there?
Our minimum's 0, 2.
Right. Our minimum value, z equals what?
14.
14. And that occurs at x equals what?
X equals 0, Y
0
equals 2.
and y equals 2. Yeah. Yep. So the minimum value is actually 14. Okay. Right. Any questions with that so far? It's pretty easy, huh? Especially when they give you the graphs.
So all you did was plotted the constraints?
Mhm.
Okay.
Yep, and found the point of intersection. And I should have included these with you. They were given to us, so you didn't actually have to do that. We will do one later for the graph. Okay.
Okay.
Yeah. All right. All right, example 3. In the maximum value of z equals 5x plus 7y, where x is greater than or equal to 0, y is greater than or equal to, subject to the constraints given in example 2. Let me ask you, what's my objective function? Isn't it the exact same as example 2?
Mm-hmm.
And if my objective is the exact same as example 2, my constraints are the same as example 2. Didn't we already plug in all of those values? The
Yes.
points of intersection? Yeah. So could you now, without even doing anything, tell me my maximum value?
51.
Yeah, my maximum value is z equals 51 at, or and that occurs
X equals 6, Y equals 3.
6 and y equals 3. Yeah. And there you go. Okay. Any questions on that? All right. Example 4. Find the maximum value of z equals 4x plus 2y, where x is greater than or equal to 0 and y is greater than or equal to 0, subject to the following constraints. So if you notice, x and y again have to be greater than or equal to 0, so we know we're in that first quadrant, right? Okay. We go to graph all of these points. Okay, so this would be x plus 2y is greater than or equal to 0. If we put it into slope-intercept form, isn't that y is greater than negative 1/2 x plus 0? So that would be this graph right here. Okay, that point right there. Okay, then y equals or greater than or equal to negative 3x plus 7. So we're up at 7, down 3, right 1, finding all of that. Okay, that's why some of these get crazy with the graphs, because you have to find where they connect, all of that. So a lot of times they'll just give them to you for that sense. Okay, now what do you notice about this graph compared to the other ones? Anyone? What do you guys notice about this graph compared to the other ones? Let me go back. Let me show you this one. Here's this graph. What's
It
different?
isn't on the y-axis.
Okay, it's not on the y-axis. Yep, yep. What else?
It keeps increasing.
It keeps increasing, right?
It's not
What
a perfect, it's not a perfect polygon.
It's not a perfect polygon. This one side is going to keep on going forever, right? They actually are not going to intersect in multiple spots, making that polygon, as Nathan said. Okay, so this actually is unbounded in a certain direction, isn't it? Yeah, so but we can still go ahead and find our values for this, and then we'll talk about something here in a second, okay? So as we look at this, okay, let's do the point at 1, 4 first. Z would equal 4 times x, which is 1, plus 2 times y, which is 4. What do we get? We get 12. Yep. Okay. At, let's do 2 comma 1, z equals 4 times x, which is 2, plus 2 times y, which is 1. And what do we get?
10.
10. And then at 4, 0, z equals 4 times x, which is 4, plus 2 times y, which is 0, and we get what?
16.
Right? Okay. Now, if we look at this, okay, we said we're not a full polygon, right? We know this is going to keep extending to the right over here. So if it's asking for a maximum value, do you think we have a maximum value if it's going to keep increasing as it goes up and up and up and up and up and up and up? What do you think?
Is the maximum value just infinite?
Yeah, there is no maximum value actually, because it is not bounded, right? Because since this line keeps going in this direction, this shaded region is going to keep increasing, keep going up and up and up and up. And whereas this one here is going to stay constant going to the right. So the maximum keeps going up, but does my minimum keep going up? Or do we have a minimum value in this sense? What do you guys think? So maximum is the highest, right? So if this keeps going up, we're never ending at the top, are we? But at the bottom here, if we look, we're bounded at the end, aren't we? At the minimum value. We are bounded here at the lowest point, right? We know we cannot get, we're talking max min, which are y values. My y's cannot get lower than 0, can it?
Mm-mm.
No, but my y's can keep going up because this line keeps extending. And if that keeps extending, my y values keep going up. Whereas here, if we keep going this way, because y can't be greater than or equal to 0, we know it has to stop at 0, right? So we have no maximum value because it's unbounded going up, right? But we do have a minimum value. Minimum, I can't even spell right now. Minimum value. And what is my minimum value of this objective? D equals what?
10.
10. Yeah. And that occurs at the point of x equals 2 and y equals 1. Okay, does that make sense on why we have no maximum, but we do have a minimum value? Because remember, maximum and minimum values are always based off of your y coordinates, right? So as this keeps going up, my y coordinates keep going up since we're not bounded in a sense. But we're bounded at the bottom here because we cannot go past y is greater than or equal to 0 at 0. Okay. All right, does that make sense in that? All right. All right, let's do an application problem now. Your favorite, your story problems. Okay. All right, a candy manufacturer wants to maximize the combined profit for 2 types of boxed chocolates. A box of chocolates covered creams yields a profit of $1.50 per box, and a box of chocolate covered nuts yields a profit of $2 per box. Market tests available resources indicate the following restraints, okay? From what they give us right now, to get our profit, our margin profit, right? Wouldn't I add my profit for my chocolate covered creams with my chocolate covered nuts? So wouldn't my objective equation be my total profit, which could be Z or P, equals $1.50. What does per box mean?
There's a variable associated with that.
Yeah, so per box. So could I take $1.50 times X, and let's let X equal the cost of, or the number of chocolate covered creams? You guys okay with that? So the profit of, if I sell 10 boxes of chocolate covered creams, when I get $1, or 10 boxes, when I get $15.
Mhm.
Yeah. Okay. Now, if I sell 10 boxes of chocolate covered nuts, I would have 2 times Y, which would be $20, right? What would I do to these two profits here to get a total profit?
Add.
I would add them up. Okay, so this is my objective equation. Okay, now let's write our restraints, our constraints. Okay, the combined production must not exceed 1,200 boxes per month. The combined production level must not exceed 1,200 boxes per month. So production, okay? So the production of X and the production of Y cannot exceed 1,200. So what does that mean?
X plus Y is lower than or equal to 1200.
Perfect. Yeah. X plus Y has to be less than or equal to 1,200. We cannot make more than 1,200 of each of those together. Okay. All right. The demand for chocolate covered nuts is no more than half the demand of the chocolate covered creams. So what is my nuts? Is that the X or the Y?
Y.
Y. No more than. What inequality is that?
Less than or equal to.
Less than or equal to half the demand of chocolate covered creams. So wouldn't that be 1/2 times X? Yeah, okay. And then the last one, the production levels of the chocolate covered creams must be less than or equal to. So creams is X, right? Must be less than or equal to 600 plus 3 times nuts. So wouldn't that be 600 plus 3 times my chocolate covered nuts? So there's my constraints. Now let's think about something else too. Okay, it doesn't say here, but if we're talking about our graph, if we go to actually graph this here in a second, okay. And honestly, I would use Desmos to kind of help us out here. That's one thing that does help with us having graphing calculators, but we can use Desmos here. If I'm looking at this, okay, if X and Y represents the number of things I make, you know, the chocolate covered creams, the chocolate covered nuts, can I ever include negative values? Can I make a negative box of chocolate covered nuts or a negative number of boxes of chocolate covered creams?
No.
No. So we also know that this X has to be greater than or equal to 0 and Y has to be also greater than or equal to 0, right? Because the production of them can't be negative. Okay, are you guys okay with that? So we know we're using that first quadrant again. Okay. All right, do you guys want me to switch over to Desmos or do you want me to just go ahead and graph these for you? What would you
Graph
like?
them.
Just graph them. Okay. So we're going to have 0, 0 here because if you look at Y is less than or equal to 1/2 X, we're going to have it 0, 0 here. Okay. It's going to be 600 comma 0. We'll have that point right there. So this is that Y is greater than or equal to 0 here. Okay. We have 800 to 400. So we have this line here. Okay. We have, and then 1050, 1050, 150. There we go. So if we use Desmos and we graph all of these constraints, this is what it's going to look like, okay? Is everyone okay with that? And if you want me to show you Desmos, we can do that after, okay? Now, if we know our objective, we have our graph and our points here. We got 0, 0 also. Can you find the maximum and now minimum values of my production?
Mhm.
Yeah. Okay. So what is our maximum monthly profit? What is my maximum monthly profit? Let's go ahead and do that. So let's do, what point do you guys want to start with?
0, 0.
0, 0. This one should be easy, right? P equals 1.5 times X plus 2 times Y. And my X is 0, my Y is 0, so my profit is
0.
all right, let's do 600, 0. The profit equals 1.5 times X, which is 600, plus 2 times Y, which is 0. So my profit at 600, 0 is $900. Okay. Let's do 1050, 150. So my profit would equal 1.5 times X, which is 1050, plus 2 times my Y, which is 150, equals $1,875. Okay. And then at 800, 400, my profit would equal 1.5 times X, which is 800, plus 2 times Y, which is 400. And we get 2,000. Okay. So now, because this is bounded, right, we do have a maximum and minimum value. Okay. So it says, what is my maximum monthly profit? So my maximum monthly profit is what?
2,000.
$2,000, right? And then it says, how many boxes of each type per month to yield that maximum profit? So normally said, well, Z is our maximum value, Z equals 2,000 because it occurs at X equals blank and Y equals blank, which is the same thing as this, okay? Because remember, our points actually, this 800 and 400, they represent something. 800 represents my X, 400 represents my Y, but what does X actually represent?
Boxes of chocolate covered creams.
Yeah, chocolate covered. So the monthly profit is 2,000, and that occurs when you sell 800 chocolate covered creams and how many nuts?
400.
400. There you go. And did you answer every question? Yeah. What is the maximum monthly profit? 2,000. How many boxes of each? 800 and 400. Okay. And obviously my minimum would be 0. That means I sell 0 of each of those or make 0 of each of those, right? And sell 0 of each of those. Okay. Any questions on that?